Okay, you can start. Thank
Mhm. Okay, but are you hearing me? Yeah.
Yes, you.
Okay. Okay. Thank you very much.
Yeah, we are seeing you,
Hello,
Santosh.
everyone. My name is Alexey Basharin, and yes, yeah, okay. I would like to talk about metamaterials beyond classical multiples. And first of all, my motivation is demonstrate new effects occurred in metamaterials, but beyond classical families like electric and magnetic multiples. And metamaterials is artificial structures with properties not occurred in nature. And for example, what is the difference between classical materials based on atoms or molecules and metamaterials? If you want to, for example, to transparent light through atomic lattice, and we cannot do it due to diffraction limit, and it means that we can't excite atoms if the size of them less than wavelengths, and but in metamaterials we can do it if we use instead of atoms meta atoms. It doesn't mean that the size of meta atoms equals to atoms, for example, if you work in microwave or in terahertz range, we can use meta atoms with size close to millimeters or centimeters. So they are based on different inclusions from metals, dielectrics, or ferromagnetics, superconductors, and so on. And they can be fabricated in a resonance manner, like split rings for excitation of different responses, like magnetic response or electric, if we want to do materials with artificial permittivity and based on some wires, electric wires. So, in the previous 20 years, it was demonstrated a lot of interesting properties of metamaterials like negative refraction, superlensing, where we can chance to see two different sources if the distance between them less wavelengths, subwavelength localization in subwavelength area. I mean, between two particles, for example, it's very nice for sensing or for photolithography, or also interesting effects of clocking. But the main elements of metamaterials is wires and split rings, split ring resonators. It means currents loop with split in this loop. In this case, we have circulated current and artificial magnetic dipole moment. If we combine two structures, we will see a negative refraction with negative permittivity and negative permeability. And but in classical definition of multiples, we have point electric dipole with electric dipole moment, and also we have magnetic dipole, point magnetic dipole with zero radius of ring. In this case, we have magnetic dipole moment, ideomagnetic dipole moment. In real sources, of course, we have some modifications, and due to imperfection of fabrication and so on. And a real electric dipole looks like this, or we have split in magnetic dipole, and we cannot characterize them only by electric and magnetic dipoles, and we need to introduce other families of multiples like toroidal dipoles and quadrupoles, and also mean square radiuses. I'll talk about them later. So, and next one is toroidal dipole, because we have toroidal helixes and solenoids, and we characterize them by toroidal dipole. So, in this talk, I want to talk about dynamic multiples and electromagnetics. I will introduce toroidal response for characterization of toroidal objects, unable states. It's a non-radiating, very interesting properties with very high Q factor and invisibility effects. And also I'll talk about some transparency effects, classification of transparency effects in electromagnetics, and present some multiples beyond of classical one, is like mean square radiuses and so on. Classical multiple expansion looks like this. We have members of electric dipole, magnetic dipole, quadrupoles, octupoles, and so on. And if you want to characterize toroidal objects, for example, with toroidal topology, we need to introduce toroidal dipole in multiple expansion. So, what is dipoles? I remind you from electromagnetics, it's a oscillation of between two charges. It's electric dipole. Current loop gives us of course, magnetic dipole. But if we excite colloidal currents along of meridians of torus, we cannot characterize this object by electric dipole and magnetic dipole, because you see that from here that magnetic fields and electric fields are the same like in electric dipole, but due to closed configuration, we can't excite electric dipole in this case. But far fields are the same. And first introduction of toroidal dipole moment and or unable states in static definition, it was by Yakov Zeldovich. He proposed toroidal dipole for explanation of slight interaction in nuclei of cesium atom, and also a lot of high energy physicists, they used this definition for characterization of some nuclear objects, and in space, for example, also we can find definition of unable states for characterization of some black holes and black matters, and in molecular physics too. So, if we talk about toroidal dipole, we see that we have very close configuration of fields, and it means that we can find that this object, we can expect that this object, toroidal object, will have extremely high Q factor with a very concentrated field. It's open resonator with very high Q factor. And it was demonstrated a lot of classical metamaterial effects like negative refraction or optical activity, and also unable states and quantum effects like Aronoff-Bohm effects and so on. So toroidal objects you can find in nature, from nuclear currents in cesium, for example, up to some fullerenes and benzone molecules, proteins, and nanotorus. And that's why we need to know about this subject, because we want to correctly characterize toroidal optics of toroidal objects, and we need to know how them interact with electromagnetic fields and so on. So also some toroidal effects, some toroidal multiples. It was introduced in one Bladel book, and in this paper of group of Carsten Rockstuhl from Karlsruhe University, they said that toroidal multiple is a part of electric dipole moment. But if we see radiation pattern of toroidal object, it looks like the same like electric dipole. So it means that if we combine two dipole modes of electric and toroidal in the same source or in the same scatter, interference between multiples gives us no radiating fields in far field zone. It means that this source will have fields, near fields only in one point of origin of this source. So first demonstration of and we called this property like anapple mode, and anapple mode was demonstrated first time in all dielectric and metallic structure here as optics, and here as microwave. And you see that in scattering spectra we have deep, very nice deep, and with it means that on this frequency we have not far field and scattering field. So if we consider fields for electric and toroidal dipoles and we combine them, we see that we have some terms with P and T dipoles. And if P equals IKT, it means that we haven't the total electric field and total magnetic field and far field zone. So they are absolutely zero. But in near field, we have a delta function of electric field, and we have magnetic field turned around of this point with zero radius. Here is conclusion that we have infinite Q factor of anapple element. Next one, next step, it was demonstrated, it was first experiment in classical electrodynamics for demonstration of toroidal response in hybrid split ring resonators and its periodic structure of them. And you see that we have closed fields, magnetic fields of magnetic field lines here, and we demonstrate here that toroidal dipoles is prevalent in system because intensity of scattered by multiples of toroidal dipoles is higher than other multiples. Means that we have a very high Q factor in comparison with magnetic resonance of second resonance, and this is very nice demonstration. After that, we demonstrated how to produce toroidal moment, dipole moment in all dielectric metamaterials based on lithium tantalate. And we also demonstrate that without taking into account toroidal dipole multiple expansion, we cannot characterize correctly transmission and reflection from these materials, from these metamaterials. And you see that reflection is more than one. It's unphysical result. So we also demonstrate near fields of this structure, and we shown that if you excite four dielectric cylinders by electric dipole in microwave, we have no radiating fields, and this is transmission, like transmission and coefficient, and we have no radiating fields, and all the fields are concentrated inside of this origin of this particle. And we measured near fields on the top of this structure, and you see that for center frequency we have we have not fields around of this structure, but for number of frequencies like this, and we have propagating fields from the source. So an apple source is it means that it's an open resonator and open resonator and with very high Q factor. So here we demonstrated far field radiation, and next step is all of toroidal and anapple metamolecules. They are 3D structures, and because we need to approximate torus by different split rings resonators and all dielectric particles and so on, but they are very complicated because for microwave, okay, we can do it, produce particles by, I don't know, it's from. In optics, it's not possible because we need to fabricate nanoparticles of complicated split ring resonators. This is only, I think, one work about this, and so the main conclusion here is that we have limitation of toroidal metamaterials, and because first of all, of course, losses, Fabry-Perot resonances, because from 3D structures and substrate we have different scattering, a lot of multiple scattering from borders, and it gives us extra multipoles in system like magnetic quadrupoles and electric octapoles and so on. They are destroyed anapole states, and it means radiating losses. But ideal anapole state is without, of course, radiating losses. So, but at first time we demonstrated that we can do planar torus. It looks like joke, but it works because we produced planar toruses from steel and by laser cutting method, and we excite this by playing wave in perpendicular direction. We could excite currents, circulated currents, and which produced magnetic field, and toroidal dipole oscillated in a perpendicular direction. So in microwave, we demonstrated that Q factor of this metamaterial is very high, approximately 3 millions in theory, and 10,000 in experiment. But I want to pay your attention that this is open planar structure, and we didn't use cryogenic temperatures. So very interesting that electric field of plane wave concentrated in between two wires, and with in subwavelength volume, and this field is more than 20,000 times than plane intensity of plane wave, of electric field of plane wave, because we focused all fields inside of metaparticles. So it's very interesting, because if you put here some nonlinear elements like I don't know, like for sensing, for example, and so on, we can excite these particles, and we can see, for example, the low volume of sensitive media. So, and it's interesting to use for modulators if we put some semiconductors and so on. So, and you see that magnetic field is not so high, but this metamaterials of electric type and with a very concentrated electric field. So we did multiple expansion, and we found that here we have interaction between electric dipole and toroidal dipole. They are in different phases, and they produce anapole states. But we have here extra magnetic quadrupoles, and this is parasitic factor, and because we have not an infinite Q factor. So next step of my talk here, I would like to talk about some interaction between multiples, different interaction. Of course, we have Fano resonance of interaction between electric dipole and magnetic dipoles moments, and it results of interaction between bright and dark modes. We have also Fano resonance between magnetic dipole and toroidal dipole. And also interesting effect like Kerker effects of suppressed forward or backward scattering. It also results of interaction between electric and magnetic dipole and magnetic and toroidal dipole. If we have interaction between electric dipole and toroidal dipole, we can demonstrate anapole states, zero scattering, and also Fano resonance if are they in phase, for example, in the same phase, and so on. So here is some interesting phenomena, because if the frequency of electric dipole and toroidal dipole are the same, we have absolutely invisible metamaterials without scattering fields. If the frequencies of electric dipole and magnetic dipole are different, we have like Fanon effects or Kercher effects with, for example, forward scattering. We have not backward scattering, but all the radiation concentrated in the forward direction. But it's an effect of scattering. It's a scattering effect. And the next one is nullifying between multiples. For example, we have series of multiples like electric, toroidal, and magnetic in system. And if all of them are zero, it can be due to interaction in compound particle. In this case, we have
Alexei,
also, yeah.
5 minutes.
Yeah.
Okay.
Yeah. Okay. Thanks. In this case, we have not absolutely scattering fields, and okay, and the incident field can be transparently passed through the system. So next step, I want to show you some interesting works in metamaterials with some interaction between and between particles in system. It's like electric anapole, and here is magnetic anapole, because in this case magnetic anapole is the result of interaction between magnetic dipole and mean square radius of magnetic type. From multiple expansion, we have 3 families of electric, magnetic, and toroidal dipoles. And also have, if we talk about interaction between far fields, we need to introduce here some interaction families. And here I show you that, for example, we have electric families and toroidal families. And if you want to nullify zeroing of scattering from the system or intensity, radiation of intensity, we need to say that this term should be 0 or this term should be 0. It can be due to interaction between electric and toroidal dipoles like anapole, and between toroidal and toroidal mean square radius is multiples of higher order. And the same situation is magnetic dipole. Here first of all, I want to say that we have toroidal dipole is results of currents inside of along of meridians of torus. And if you imagine torus of next generation, it looks like here. I try to explain you. This is old telephone cable, and if we add it on the torus and long of torus, it looks like mean square radius of magnetic type. The next step, if we take toruses and round of torus and round of mean square radius, it gives you toroidal mean square radius or toroidal of third type. So this is geometrical definition of next type of toruses, and they looks like coronavirus, for example. It's like torus, and some viruses looks like mean square radiuses. So here is a table. Here is I would like to like conclusion to present some interaction between multiples. For anapole states of electric type, it's interaction between electric dipole and toroidal dipole. Magnetic anapole, it's magnetic dipole and magnetic mean square radius. And toroidal anapole is results of toroidal dipole and mean square radius of toroidal dipole. So my conclusions here is that we have some very difficult interaction between parts of multiples in system, but it looks like, for example, for toroidal dipole and moreover for mean square radiuses of toroidal type and magnetic type, it doesn't possible to excite them in metamaterials. But it's not true, because they can be excited with low intensity in different, for example, in disk or with in particles with very high Q factor, with very high permittivity, like strontium titanate and so on. There is toroidal mean square radius can be excited in microwave, for example, or in terahertz. So, but if you want to present some invisible particles or some transparent particles, we must to know how to excite them and must know about electrodynamics of them. So, and in my conclusions here, I talking about dynamic multiples and electromagnetics, and I presented here some application of nabble states and toroidal response in electromagnetics, and I introduced some multiples like mean square radiuses and so on, and also we're talking about classifications of transparency effects in electromagnetics. Thank you for your attention.